there, chemists. In this lesson, we're going to recap what we said last time about conductors, semiconductors, and insulators. We're going to learn how we can calculate incoming incident beams of energy based on band gap energies, and then close up with how we can change the properties of semiconductors by doping them with impurities to change their properties. So first off, on your notes, I have a picture that abbreviates what we looked at last time. Remember last time we talked about atomic orbitals combining to make these bands of orbitals in the sea of electrons. And instead of drawing a whole bunch of horizontal lines to show the conduction band and the valence band, we're just abbreviating them with a box. So this is our valence band and this is our conduction band, and here we have the band gap. Now when we have an incident beam of energy, we create a promoted electron and we also create what's called a hole, which is abbreviated with an H and a plus charge. And those both count as charge carriers, a space where an electron used to be, and then a newly occupying electron in the conduction band. And it's all about this band gap energy, which is unique for different elements or alloys, etc. Speaking of conduction, remember we said that good conductors have very small band gap energies, usually less than an electron volt. Insulators, conversely, have large band gap energies, maybe greater than electron volts. Depends on what source you look at, but that's a rough approximation. And semiconductors lie in between, and it's all about promotion of electrons from the valence band to the conduction band. So one thing we didn't talk about last time is what if your energy is not exactly equal to the band gap energy? What happens to that excess energy? So here it says we have an electron beam that's striking a crystal of cadmium sulfide. The electrons are scattered, and then they move at a velocity of 4.4 10 to the 5 meters per second. The band gap energy was 2.45 electron volts, and an electron's small, 9.11 10 negative 31. Well, what was the energy of that incident beam? Was that exactly equal to the band gap, or was it more than enough? I want to calculate what that is. So what's actually happening here is you have an incident beam with some energy, and that's what we're asked to calculate. We are crossing the band gap energy, but then we also have these scattered electrons, and as a result they move. So this is analogous to the photoelectric effect, where you shine light on a surface and it has enough energy to excite an electron through some quantized amount of energy. The extra energy goes into kinetic energy, energy of motion of that charged particle. So our total energy here, of what's coming in, is the band gap energy plus the kinetic energy, which is 1/2 mv squared. The band gap is given 2.45 electron volts. And I know my mass of my electron, I know my velocity of my electron. So it's 1/2 the mass, 9.11, 10 negative 31 kilograms. And the velocity, which is 4.4 10 to the 5 meters per second. And then I have to square that. Now, if I just plug those numbers in, I'm not going to get an answer that makes sense because my units are not compatible. My electron volt is what the band gap is given in. MV squared over here, kilograms times meters per second squared, that's a joule. So I need to convert that joule into an electron volt. And I can do that using the conversion we learned in the previous lesson. I'm just going to write it off to the side here. There's 1 electron volt for 1.6 10 neg 19 joules. When I plug that in, the 2.45 electron volts gets added to 0.55. That's how much more energy apparently was given as kinetic energy. So you get a perfect 3.00. So that's just a way we can talk about what happens to that extra energy. It's kinetic. We can quantify it based on how fast it's moving and indirectly solve for how much energy was coming in. Okay, so I just want to wrap up by talking about semiconductors a little more closely and how we can alter their properties by creating impurities. So this is called chemical promotion, and this creates charge carriers, those free electrons or holes, by introducing an impurity. Don't let the word impurity fool you. Impurities can be bad, we call those contaminants, or they can be good, and we call those dopants. So what we're about to see here is an example of doping a semiconductor to make its properties better, or at least change them the way we want to change them. So chemistry is all about changing things and controlling those changes. So we can do one of two things. You can either incorporate atoms with one less valence electron, or you can incorporate atoms with one more valence electrons. Those are respectively called N-type and P-type semiconductors. And I just want to show a picture of what that looks like. Starting with a regular semiconductor, let's look at silicon. And you have to imagine a large array of silicon atoms all connected to each other in a giant silicon crystal. And what's semiconduction? Well, semiconduction is taking your valence band and promoting an electron up to the conduction band and having a perfect band gap to do that on its own. But we can change that. We can change that to be what's called an N-type or a P-type semiconductor. And let's go through one of those, each of those one at a time. An N-type, it says it above, is when you have one more valence electron. So instead of a silicon, let's change one of the silicon atoms to a phosphorus. But imagine that most of the crystal is still silicon atoms. What that does is it creates an extra layer of energy levels right below the conduction band. So we have an extra layer of energy levels. In that smear of electron bands that we look at. So your electron promotion is actually just from that up to the conduction band. So that changes the conductivity of a phosphorus doped silicon semiconductor. And just as a side note, it's very interesting, I think, how they make these. There's a variety of ways, but this is analogous to making an alloy, where you are replacing one of the atoms with another atom. So this is a substitutional alloy. Just as a refresher on alloys, alloys are solid mixtures that behave like metals. So for example, you could mix copper and zinc and you get what's called brass. Two metals mixed together in a substitution alloy gives you the alloy brass, and its properties are very metallic. It doesn't have to be two metals. Another very commonly known alloy is iron and carbon. That makes steel. This is actually an interstitial alloy, and it still behaves like a metal, so we still call it an alloy. It's a solid mixture that behaves as a metal. How they do doping with silicon, I learned, is that you can replace silicon atoms by actually transmutating them. So I find this just interesting. Made with transmutation. That's a word that means we changed the element into a different element. And one way they do this is you can imagine having silicon isotopes, let's say silicon 30, bring it near a source of neutrons, which have no charge but a mass, and it forms much less stable silicon 31 isotopes. None of these are the major isotope of silicon, but some of them still exist in naturally occurring silicon, and this is how this works. Then silicon 31 isotopes will spontaneously undergo a beta decay, and that's how you transmutate them into phosphorus atoms. Beta decay is when a neutron becomes a proton and you spit out a beta particle. So that's how we can take some silicon atoms and artificially turn them into phosphorus atoms. It makes it very uniform, the substitution, but I found that to be a very interesting application of nuclear changes that we only really learn about a little bit in chemistry. It's really more physics, I would argue. So that's what an N-type semiconductor looks like. Let's just look at one other, the P-type. A P-type semiconductor is when you have one less valence electron. So instead of silicon, we could have something like a boron atom embedded in the silicon crystal. You still have your conduction band, you still have your valence band. However, unlike an N-type semiconductor, which created this extra layer of energy levels from the extra electron, this creates holes which still act as charge carriers, but it creates holes because of the fewer electrons. And as a result, our electron promotion is just from the valence band into those holes. That's what it means to be a charge carrier in that case. Okay, so that's just a very, very brief overview of how we can change the properties of semiconductors, how we can calculate energies based on band gap energies and the kinetic energy related to moving particles, electrons in this case, and a recap of what the difference between a semiconductor, a conductor, and an insulator is.